Hello Calc 3, welcome back to another video. In this video we will be starting the journey through chapter 15 where ultimately the goal is to generalize the integral from Calc 1 and Calc 2 to multivariable functions, which we just got done talking about in chapter 14. And in particular in section 15.1, which we'll be covering today, we're going to talk about double integrals over rectangular regions in the plane. So remember that in Calc 1, we took definite integrals over closed intervals. So the definite integral of some function f of x over the closed interval from a to b was given by this expression here, which of course we are all familiar with at this point. But remember that the definite integral gave the signed area between the curve y equals f of x in the plane and the x-axis. So in that little diagram I have drawn below, I have the curve y equals f of x drawn into the plane, and then I have the endpoints of the closed interval a and b along the x-axis. And the definite integral is going to give us that area in red, where remember that this area over here that's underneath the x-axis will be negative, which is what I mean by signed area between the curve y equals f of x and the x-axis. So analogously, the double integral for a function f of xy in two variables will give the signed volume between the surface z equals f of xy and the xy plane. So I did my best to draw what that would look like. So let's say that z equals f of xy gives this green plane that I have drawn in space above the xy plane. And let's say we want to take the double integral over the region R, which is given by that rectangular region inside of the xy plane in yellow. Then the double integral will give us the volume between the two planes, between the green plane and the yellow region down in the xy plane. And just like we did in Calc 1, we're going to end up defining the double integral by taking the limit of Riemann sums. But instead of taking Riemann sums of rectangles like we did in Calc 1, we sum the volume of rectangular prisms. This should say the volume of rectangular prisms that estimate the signed volume beneath the surface. So let's get into how we're going to build up this notion here. So this next section is really going to be somewhat of an abstract description of what the double integral is so that we can build it up, give it a definition, and then after we're done with that, we'll get into calculating double integrals so we can actually find the volume under different surfaces. So again, in this section, we only look at double integrals over rectangular regions in the plane. In section 15.2, we will generalize this notion to different kinds of regions in the plane other than rectangular regions. And for all of this discussion here, where I'm building up the definition of the double integral, let's assume that f of xy is a continuous function, and it's defined over the rectangular region R, where x is between a and b, and y is between c and d. It is true that there are functions that are not continuous that are Riemann integrable. But for the sake of simplicity, I'm just going to be talking about continuous functions all the way through this lecture. I'm not going to worry about functions that have an integral that aren't continuous. Maybe it'll pop up later, I don't know. But for now, let's just worry about continuous functions. So again, the function is going to be defined at every point inside of this region, and this region is given over here, so you can refer to this picture multiple times as I'm going through a bunch of these points here. And we can subdivide the region R into a bunch of smaller rectangles using lines that are parallel to the x and y axis. Again, you can see the grid that we formed that splits up the region R in the picture. And we say that the grid divides our region R into n smaller rectangles. So let's just say there's n of them. And these n rectangles define a partition of R. So by partition of R, I just mean that we're subdividing R into a bunch of smaller pieces such that when you take the union of all of those pieces together, you get back the big region R. And each small rectangle has area given by, and we'll denote it by this delta A here. And delta A will be equal to delta X times delta Y, where delta X is the width of the rectangle. So again, if you look back up to our region here, you can see I already have an arrow pointing to that special rectangle. You can see that delta x gives the width of that rectangle and delta y gives the height of that rectangle. And we define delta A to be the width times the height. So delta A gives the area of each of these small rectangles. We can also number all of the small rectangles inside of the region. So let's just say we call them R sub 1, R sub 2, up to R sub n. And once we've numbered them, then we can say that the area of specifically the R sub kth rectangle is given by delta A sub k, where again, delta A sub k will equal delta x sub k times delta y sub k. So the area is just the width of the kth rectangle times the height of the kth rectangle. And once we've defined this, then we can start making Riemann sums. And to make Riemann sums, we pick some point, x sub k, y sub k, in each of the small rectangles r sub k. And we can pick different points inside of the rectangle. So if you look up to the special rectangle that's given in red here, notice that the point x sub k, y sub k that's been selected is not in the center of that rectangle. You can actually pick any point inside of that rectangle. And we are ultimately going to sum up the volumes of all of the rectangular prisms that are given by the area of each of the small rectangles multiplied by f of x sub k, y sub k. So this f of x sub k, y sub k will give the height of the rectangular prism out of the plane, and this delta A sub k will give the area of the base rectangle for that rectangular prism inside of the plane. So that'll give us the volume of the rectangular prism. And the Riemann sum is going to be the sum of all of these different volumes for each of the small rectangular regions that are subdividing our region R. So we denote the Riemann sum as S sub n, where n gives the number of rectangles that we are subdividing the region R into. And that'll be the sum from k equals 1 to n of each of the volumes associated with each of the rectangles. Or if you want to expand that, that v sub k, you can also write it as the sum from k equals 1 to n of the height of those rectangular prisms multiplied by the area of each of the small rectangles that are subdividing R. And our choice for the point inside of the rectangles could change the value of this Riemann sum. But the nice thing is that once we make our partition of the region really, really small, so that all of those small rectangles in the plane are infinitesimally small, they get smaller and smaller, the choice of x sub k, y sub k ultimately won't matter. So once we take the limit of these Riemann sums, our choice of x sub k, y sub k isn't going to change that limit. We're not going to go through a proof of that, but it is the case. So each of these Riemann sums will give an estimate for the signed volume under the surface, and as this partition of the region R gets finer, meaning that there's more and more small rectangles, the estimate will get better and better. So this is analogous to Calc 1 as well, where you sum up the area of more and more rectangles and your estimate will be getting better. And before we move on, I should give a little bit of a definition here. So the norm of a partition of our region R, so let's say we have a partition P, then the norm of that partition P is going to be given by this expression here, which I have underlined in purple and now red. And it is a number such that the height and width of all of the rectangles inside of the partition are less than or equal to this norm. So for all of the rectangles, the height and width of those rectangles is going to be smaller than the norm. So let's say that the norm is equal to 1 for our partition. Then it means that if I take any rectangle out of the partition, then the width of that rectangle will be less than or equal to 1, and the height of that rectangle will be less than or equal to 1. So we can take the limit of the Riemann sums as the norm of the partitions is going to 0. So this looks like this expression that I have down here. We have the limit as the norm of the partition goes to 0 of the sum from k equals 1 to n of f of x sub k, y sub k times the area of the kth rectangle. And we can also write that as the limit as n goes to infinity of the same sum, where it's understood here that when I say the limit as n is going to infinity, it implies that the norm of the partition is going to 0. Because as the norm of the partition is going to 0, we're ending up with more and more rectangles that are subdividing our region here. So we could write it either way. And when this limit exists, we say that the function f of xy is integrable over the region R. And this limit is defined to be the double integral of the function f over R. So as I said earlier, not every function will be integrable. There will be times when you can make as many Riemann sums as you want to, but the limit of those Riemann sums as the norm of the partition is going to 0 will not exist. And when that's the case, we say that the function is not integrable. But we will not be worrying about those functions because, of course, we want to develop the theory of integration, and to do so, we need functions that are integrable. So when this limit exists and the function is integrable over R, then that limit will be the double integral of f over R, and we write the double integral of f over R with these expressions here. So either one would be fine. You write two integral signs sub R, where R is that region that we're integrating over, of f of xy dA, or you could write it as the double integral sub R for our region R of f of xy dx dy. Either notation is absolutely fine. All right, so now that we've built up the definition of the double integral, I do want to talk about a little bit more of the intuition for the double integral. So viewing the double integral as the volume under a surface. So if we have a function in two variables, f of xy, and that function is positive over all of some rectangular region R in the plane, then the double integral of f of xy over the region R will give the volume under the surface given by z equals f of xy. So if you look at this diagram all the way on the left here, we have our surface in three-dimensional space here. We also have the region R given in the plane, this rectangular region. And then you can see that the red rectangular prism corresponds to one smaller rectangle that is subdividing the larger region R in the plane. So that's what we're taking the volume of those rectangular prisms, and the Riemann sum takes the volume of all of those rectangular prisms and adds them together. And then as we take the limit of those Riemann sums, you can see with the diagrams on the right here, when n gets bigger and bigger, or the number of small rectangles in our partition of R is getting bigger and bigger, the estimate for the volume under the curve is going to be getting better. So as the partition gets finer, you can see that the estimate is going to be getting better. And the volume under the surface over the region R is going to be called the total volume of the solid. And again, that volume is given by the limit of the Riemann sums as n goes to infinity, which we have defined to be the double integral of f of xy over R. And where dx dy is going to 0 as n goes to infinity inside of this double integral here. Because again, as n goes to infinity, it's assumed that the norm of the partition is going to 0. So all of those rectangles in the region R are going to be getting smaller and smaller, which means the width and the height of those rectangles will also be getting smaller. Okay, so now that we've talked about the definition of the double integral, and we've kind of built up an intuition for what it means geometrically, the next item on the agenda is figuring out how to actually calculate these things. So we haven't really talked about that, but we can move into that now. So let's say that we have a function z equals 4 minus x minus y, and this gives us a plane in space. And say we want to find the volume under the plane over the rectangular region R, which is the region where x is between 0 and 2, and y is between 0 and 1. So again, all of these things are drawn inside of, I shouldn't say drawn, I stole this picture from the book, but it's all inside of this diagram over here to the left. So we have our function z equals 4 minus x minus y graphed in green. And then we have our rectangular region boxed out in white in the xy plane down at the bottom. And notice that we can slice through the plane z equals 4 minus x minus y with planes that are perpendicular to the x-axis. So that plane is given in orange in the diagram here. And once we slice through the plane with that orange plane perpendicular to the x-axis, we can find the area of each of those slices, or each of those cross sections that's under the surface z equals 4 minus x minus y. So notice that when we take our plane perpendicular to the x-axis and we slice it through the plane z equals 4 minus x minus y, there is a curve of intersection of those two planes. And that curve of intersection is going to be a curve inside of the plane x is equal to 1 in this case, because the cross section we have in the diagram looks like it's x equals to 1. And so we can use methods from Calc 1 to give us the area of that cross section. So the area for each of those slices, or each of the cross sections, is given by the integral from y equals 0 to y equals 1 of 4 minus x minus y dy. So that's the expression I have over here. And depending on what cross-section we're taking, so what the cross-section corresponding to what value of x, we're going to get a different area. So depending on what curve we get when we intersect the cross-section with the curve z equals 4 minus x minus y, it'll give us a different area. And we can define a function that takes us from the x value corresponding to our cross-sectional plane that pops out the area underneath that cross-section intersected with the plane z equals 4 minus x minus y. So the volume under our entire surface then, looking at these cross sections now, is going to be given by the integral from x equals 0 to x equals 2 of a of x dx, right? So intuitively what's happening here is we take cross sections that are perpendicular to the x-axis, we slice them through our surface, and that allows us to find the area underneath the surface inside of each of these cross sections. And when we take the integral from x equals 0 to x equals 2 of all of these different areas, we are basically adding up all of the areas of these cross sections to get the volume underneath the whole surface. So in this case, the volume is going to equal, as we already said, the integral from x equals 0 to x equals 2 of a of x dx, where that a of x function gives us the area for different cross sections perpendicular to the x-axis. And then we can do a little bit of substitution here. So we know what that function a of x is equal to. That's equal to the integral from y equals 0 to y equals 1 of 4 minus x minus y dy. And now we can evaluate the integral from y equals 0 to y equals 1 of 4 minus x minus y dy. To do so, it's going to be very similar to the way that we did partial derivatives. So because we are integrating with respect to y, we treat x as if it's a constant, and then we integrate. So just like normal, the integral of 4 is still going to be, or the antiderivative, I should say, of 4 is going to be 4 times y. The antiderivative of minus x is going to be minus x times y. And the antiderivative of minus y will be minus 1/2 y squared. And because this is a definite integral, we're going to evaluate this expression at 1 and then subtract the expression evaluated at 0. So the expression evaluated at 0 will just be 0, because we're going to have 4 times 0 minus x times 0 minus 1/2 times 0. So we only have to worry about what happens when we plug in 1. But if we plug in 1 for y, then we get 4 minus x minus 1/2. So notice that now this x is showing up inside of this next integral. And so once we have 4 minus x minus 1/2, we can make it look a little bit nicer. So it's just 7/2 minus x. And now we have just a regular integral in one variable. So we're taking the integral from x equals 0 to x equals 2 of 7/2 minus x dx. And at this point, it just becomes an exercise from Calc 1. So the integral of 7/2 will be 7/2 x. The integral of minus x will be minus 1/2 x squared. And we're taking this integral from 0 to 2. So again, we plug in 2 and then subtract what we get when we plug in 0. And this gives us 5. So ultimately, the volume under this z equals 4 minus x minus y over the rectangular region where x is between 0 and 2 and y is between 0 and 1 is 5. And in other words, if you want to get rid of some of the way that we kind of developed this, the volume will just be equal to this repeated integral here, or iterated integral, where we have the integral from 0 to 2 of the integral from 0 to 1 of 4 minus x minus y dy dx. And notice that since we are integrating in this case with respect to y first, the dy is going to go inside of the dx. That's to notate the fact that this integral right here is going to be with respect to y as opposed to x. If you would switch the dy and the dx here, you would actually get different expressions or different values. But now, a natural thing to ask is, could we have used cross sections that were perpendicular to the y-axis instead? So the cross sections up here are perpendicular to the x-axis, and then we're taking the integral of all of these different areas of our cross sections. But can we do the same thing where we take the cross sections perpendicular to the y-axis, and the answer ends up being absolutely yes. Yeah, we can do that. So again, we have our plane z equals 4 minus x minus y given in green. We still have our rectangular region. And this time we have a cross section that is perpendicular to the y-axis. And the area of that cross section that's bounded above by the plane z equals 4 minus x minus y is given by the integral from x equals 0 to x equals 2 of 4 minus x minus y dx. So in this case, we're going to be integrating with respect to x first. And the volume under z equals 4 minus x minus y over the region R will be given by the integral from y equals 0 to y equals 1 of this function giving us the area for different y's with respect to y. And again, doing a little bit of substitution now, the volume will equal the integral from 0 to 1, and then the integral from 0 to 2 of 4 minus x minus y dx dy. And so we're going to evaluate the inside integral first. So this integral with respect to x. And again, we do it just like we did with partial derivatives. So we just treat y like a constant and then integrate. And we get 4x minus 1/2 x squared minus xy. And again, we're evaluating at 2 and then subtracting when we evaluate at 0. Again, if we evaluate at 0, we get 4 times 0 minus 1/2 times 0 minus 0 times y, which is just going to be 0. So we're just interested in what happens when we plug in 2. And we get an 8 minus 2 minus 2y. And now, again, this just becomes an exercise from Calc 1. So it's just a single integral here. So we have the integral from 0 to 1 of 6 minus 2y dy. And that'll give us 6y minus y squared from 0 to 1, which is equal to 6 minus 1, which is equal to 5. And so ultimately, regardless of which cross sections we used, we got the same answer. So we can get the same answer when we integrate in the opposite order. And in fact, this is generally true. So it's not just true for our example, it's true for all continuous functions f of x, y. And this is called Fubini's theorem, specifically the first form of Fubini's theorem. So if we let f of x, y be some continuous function throughout a region R, a rectangular region, where x is between a and b and y is between c and d, then the double integral of f of x, y over R is equal to this iterated integral where we have the integral from c to d and the integral from a to b of f of x, y dx dy. So notice here we're taking the integral with respect to x first, and then taking the integral with respect to y. And that will also be equal to the same integral where we've reversed the order of integration. So notice that in the second integral, we're taking the integral with respect to y first from c to d, and then taking the integral with respect to x from a to b second. And again, Fubini's theorem tells us that we can do the integral in either order. Either one will be fine. It'll give us the same answer. Okay, and finally, the last thing to go through for the video is just a couple of examples of double integrals. So let's say we want to calculate the double integral of f of xy over the region R, where f of xy is equal to 100 minus 6x squared y, and R is the rectangular region where x is between 0 and 2, and y is between -1 and 1. Well, by Fubini's theorem above, this double integral over R of f of xy will be equal to the following iterated integral, where we're integrating with respect to y first and x second, just because I chose to do it that way. Again, Fubini's integral says we can do it in either order, so I just chose to integrate with respect to y first. And we evaluate the inner integral first. So we have the integral from -1 to 1 of 100 minus 6x squared y dy, and we just treat x like a constant and integrate. So we get 100y minus 1/2 times 6x squared y squared from -1 to 1. And we can plug in 1 and -1. And we get this 100 plus another 100, and the minus 1/2 6x squared plus 1/2 6x squared will cancel with one another. And we're just left with the integral from 0 to 2 of 200 dx. And again, this just becomes Calc 1 at this point. So the integral of 200, or the antiderivative of 200 will be 200 times x, and we're evaluating from 0 to 2, and that'll give us ultimately 400. And I didn't put it in here, but if you were to integrate in the opposite order, you would get the same answer. You'd also get 400. I think your book does it both ways. You can check out the other direction if you'd like to do that as well. And then finally, the last example for the video is similar. So we just want to find the volume of the region bounded above by z equals 10 plus x squared plus 3y squared, and below by the rectangle R, where x is between 0 and 1 and y is between 0 and 2. So the volume, as we've mentioned from before, is equal to the double integral of f of xy over the region R, and by Fubini's theorem, that will be equal to the following iterated integral over here. And we will worry about the inner integral first, where again I have decided to take the integral with respect to y first as the inner integral. And the integral of 10 plus x squared plus 3y squared with respect to y is 10 times y plus x squared y plus y cubed, where we are evaluating from 0 to 2. And we can plug in 2, and we get 20 plus 2x squared plus 8. And if we plug in 0, we just get 0. So ultimately, we end up with the integral from 0 to 1 of 28 plus 2x squared dx. And again, this is just Calc 1 now. So that integral will be equal to 28x plus 2/3 times x cubed from 0 to 1. We just plug in the 1, and we get 28 plus 2/3. And simplifying a little bit, that gives us 86/3 as the value. So even though maybe building up the definition of the double integral was a little bit difficult to understand, possibly, with some of the mathematical language going on there, ultimately calculating the double integrals, at least for this section, should not be too difficult. It's really just taking concepts from Calc 1 and applying them a couple of times. So when you integrate, you're taking one integral from Calc 1 where you're treating a variable like a constant, and then after that you're taking another integral where now you've just reduced to a function of one variable. And so there are a few homework questions that I've assigned on this, but the homework shouldn't take you too long, and you can look for that on Blackboard. And section 15.2, or the video that I'll be giving on it, will be up sometime later today. So you can look forward to that.